Yeah, okay. Thank you, Leslie, for the kind introduction. And I would also like to thank Benghai and Mars for putting together this very nice workshop, which is particularly interesting for people like us who are just starting to move into the field of these Dirac materials. And since we are new to this field, I want to put up the slide to give you actually an idea what we are usually interested in. So we are interested in ultra-fast spin phenomena at surfaces, interfaces, or in general, in condensed material. So this means in more concrete ideas, what we are usually interested in are the static and dynamic properties of spin-textured materials, for instance, in surface alloys where the rush-bar effect leads to a spin-polarized surface band structure, or in ferromagnets. In particular, we're also working on how we can tune the static and dynamic properties at these surfaces using organic materials. And furthermore, we have also started to look at correlate electron systems where we can study optically induced phase transitions or optically induced phase transition in pure ferromagnets. So in general, we are interested to understand and control the ultra-fast properties of materials. And the first point when we got in contact with these Dirac materials was when we were looking for new surfaces with high spin texture where we can put our organic adsorbate on top. And starting from this, we somehow tried to enter this field. And at the beginning, when you come from outside, we had probably a very and too naive view on these materials. So I will not stress the properties, but for us, what was interesting is that in these Dirac materials, we have this, for instance, in these graphene-like materials, we have the linear dispersion here at the K and K prime point. And the second type of class, which is the Dirac materials, are the topological insulators, where we have these surface states here, which connect the valence and the conduction band. And for us, what was interesting is to look at the spin polarization in these materials. And if you consider graphene, there at the Dirac points, we only have pseudo spin, so we can measure no spin polarization due to Lind's low spin orbit coupling in carbon. But we have a certain spin polarization in the Dirac materials. And besides putting organic molecules on top, we were asking what can we contribute to this field. And this is some ideas which I would like to present today. So we come from the area where we do angular resolved photoemission with the additional degrees of freedom, which is time and spin. And as it has already been introduced in the first talk today, so in time and resolved photoemission, the idea is to use optical light to excite electrons from the occupied to the unoccupied part of the band structure, for instance, in the unoccupied part of these Dirac cone-like states, and then measure the dynamics of these electrons. But time-resolved and also spin-resolved experiments are rather challenging, and therefore we started with something more simple, to start with just conventional angular resolved photoemission, and I will give you later an outlook what we think we can do with time-resolved photoemission. So what we want to do is, or what we are started to do is to do angular resolved photoemission on Dirac materials or Dirac-related materials. But as it was already pointed out this morning, if you do angular resolved photoemission, there's also a catch. So if you use such an hemispherical analyzer and you have a material with a large Brillouin zone of several reciprocal angstrom, the problem occurs that due to the limited acceptance angle of these detectors, you only measure the band structure in a very small range of the Brillouin zone. And then if you want to measure all the Brillouin zone, you have to tilt the sample. And for instance, if you think of our dichroism experiments where the geometry really matters, this can lead to a problem since you, by rotating the sample, you will constantly change the incident angle between the light and your sample. So therefore is the question, can we contribute? Is there another way of doing RPROS? And if I pose a question like this, so there is. So this is something which is coming up, which is called or was called momentum microscopy. And this is a technique which has been really pushed in the last year by the group of Jürgen Kirschner and in particular Christian Tusche in Halle, and also here in the house by the group of Gerd Schönhense. And there you do angular resolved photoelectron spectroscopy using a photoemission electron microscopy, so PEM optics. And to make it very simple and very brief, I will not go into the details of electron optics, but you can think about this PEM like in an optical microscope. So you have, instead of you image not light, but photoelectrons, and in the end, the ejected photoelectrons are projected by lenses, and you get a magnified image of the real space of your sample. So how can I now do RPROS with this type of detector? So I can also think again in the analogy of optics. So if I have a conventional microscope, I have lenses, and if I have an object here, the rays which leave the sample at identical takeoff angles will intersect in the back focal plane of this objective lens, or of this lens. And if I consider different takeoff angles, I will see that for each takeoff angles, the rays which are emitted from all over the sample, but with one takeoff angle, will intersect in different points here in the back focal plane. So if I want to have this momentum space information or this back focal plane information, what I have to do is I do not have to image with my lens the image plane, but the back focal plane. And this I can do with such a momentum microscope or with such a beam optics. If I image the back focal plane, I get a direct access to the momentum space distribution of the photoelectrons that are emitted from our sample. And this is a very efficient way of doing ARPUS, since we get the entire distribution of photoelectrons in momentum space for a given photon energy. And since for ARPUS we do not only need the momentum space resolution, which is given by the photoemission electron microscopy optics, we also need an imaging energy filter which preserves the momentum space information during the energy filtering process. We have some projector here, and then we get so-called constant binding energy maps, which is the momentum space distribution of the electrons for one given kinetic energy. And then if you change the potential of our detector, we can basically sweep through the entire band structure and get three-dimensional photo emission data cubes, which we then afterwards in the data analysis can slice in arbitrary directions and thereby get cuts through the band structure of our material. So momentum microscopy in principle is an ideal tool if you want to study the band structure of materials with very large Brillouin zone. And also what we should not forget is also we can study them with very high spatial resolution of a few hundred microns, since after all this machine is still a microscope. And with this technique at hand, or also with conventional ARPUS, I will show several examples what we have done in the last 2 years in the field of Dirac-like material. So we had one project which was initiated by Binghai, where we studied again the surface states of noble metal surfaces and somehow wanted to connect these surface states to the framework of the topology, which is known for topological insulators. Then we are also trying to work on new 2D very thin materials. I will show you our approach or our results where we want to grow styrene on gold. And in the end, if there's still time, I would like to give you a brief summary of our project that basically initiated this Dirac business, where we try to functionalize a topological insulator by organic molecules. So let me start with the first project where we were thinking about, or which was initiated by Binghai, and where he thought about the Shockley type surface state of a noble metal like gold, silver, or copper. So as you all know, on these surfaces, we have within the bulk band structure, if you project them on the surface, we have this famous L band gap, where we have here the S band, the P band, they cross, and in this projected bulk band gap, we have the occurrence of a Shockley type surface state. And this is well known, and this is for textbooks, and they have been studied for detail. When we now have a heavy metal atom such as gold, for instance, we have a large spin-orbit coupling, which, if you consider the bulk band structure, leads to a small opening of a gap. But if you now consider again the surface states, they are usually not described in a model that considers the bulk band structure, but they are usually discussed completely decoupled in a way that in the description we just introduce a Rashba type part in the Hamiltonian, which leads to momentum space splitting and therefore to a spin splitting of the surface state. And in order to connect this spin splitting, or this momentum space splitting here, to the band structure itself, Binghai started to do a full calculation, DFT calculation of the gold band structure, which includes spin-orbit coupling. And here we see the result of the bulk band structure projected on the surface of the 111 direction. And what we see here, we see the bulk bands. We see here the L band gap. And within this L band gap, we see the formation of a surface state which has a certain spin polarization, which is shown here in red and in blue color. And if you look at this data or this calculation in more detail, we see here below the Fermi level, so in this regime here, which is blown up over here, we see two parabolic-like states which are shifted in momentum. And this is, first of all, basically what we also measure in the experiment. So here we see ARPUS data of the gold surface state. We see nicely the Rashba spin splitting, and we see a parabola dispersion which matches the free electron-like model and Rashba model, which which has been known for some time. And here I would also like to mention that we are not the first who measure this occupied part of the band structure. So this is measured thousands of times, for instance, even with higher resolution by the group of Friedel Reinhardt in Würzburg. The peculiar part which basically caught our attention is here in the very high unoccupied part of the band structure. So if you look very closely, you see that the surface state does not just go disperse upwards like these parabolas, which are shown here, but they somehow bend and move into the bulk bands of the gold surface. And if you look very closely and use your imagination, you get the feeling that, for instance, this red band goes from the conduction band into the valence band on this side, and vice versa for the blue one. So if you really use your imagination, you can get the impression that it looks like the surface state of a topological insulator which connects the bulk and the conduction band. And we also, I agree here you have to use your imagination, but what we then did, or what Binghai did, is he artificially increased the spin-orbit coupling in the material. You see then that this gap here, which is infinitesimally small in the real gold, opens up, and then you see that the band structure gets more distorted, and the surface states really look like the surface state of such a topological material. So this is a nice toy model, or was in the beginning a nice toy model, but if you want to look at something like this, the question is always, can we experimentally prove this, or can we get experimental proof that the band structure really starts to bend here and that its calculations are really valid? And at this point, Benghai and Claudia Felser contacted us, and we did 2 photon photoemission experiments using femtosecond laser sources, which we frequency doubled in order to access the entire band structure in the unoccupied part of the Brillouin zone. And what we then did is we did a 2 photon photoemission experiment using a photon energy very close to the difference between the vacuum level and the Fermi level. And since we want to measure the entire band structure, we used our momentum microscope in order to collect as many photoelectrons as possible. And here we see, for instance, such a constant intermediate state map of the unoccupied band structure. You see a lot of features, since the 2 photon photoemission process does not only capture the occupied, but not only the unoccupied, but also the occupied states. So we see, for instance, here in the center, we see the replica of the occupied surface state, which is an electron transition from the occupied state by the first photon into a virtual intermediate state, and then it is kicked out above the vacuum level and is then detectable. The other excitation path is from a bulk state into the unoccupied part of the surface state, and then it is kicked out, and this is the state we see here, unfortunately very faint on this projector. And what we then did is we did not this measurement only for one intermediate state energy, but we followed the dispersion of all the bands for all possible intermediate state energies. For instance, here, this circle, which disperses outward in momentum, is the unoccupied part of the surface state. And to compare our measurement to the calculation, what we then did is we determined the radii in momentum space of all the features, here for the unoccupied part of the surface state, here for the occupied part of the surface state, and then we plotted them over the band structure calculation. And first of all, what we see is that if we consider again the occupied part, which we measured and is plotted now and down here, we see that it more or less follows the dispersion of a parabola, and that the effective band mass of this parabola nicely fits to what has been measured beforehand, for instance, also by Friedel Reinhardt and other people. If we go higher to the intermediate state values here in this intermediate state range and plot the parabola further, we see here a first deviation from this parabolic dispersion. And this has also been seen beforehand, for instance, by the Donald group using inverse photoelectron spectroscopy. But what was really new and has not been accessed beforehand is the part up here. And there we see that we have a further kink of the band structure of the surface states towards the bulk. And if we, on this side, not only compare it to a parabola, this parabolic dispersion, but also to the calculation which we have performed in Dresden, we see that our dispersion of the unoccupied part of the surface state nicely fits to what has been predicted by the density functional theory calculation. So what does this mean in the end? And so this means that we can, when we start with a noble metal surface, this Shockley surface state, and we have the strong spin-orbit coupling, we can not only understand the Rashba type spin splitting of this state just by adding a Rashba term, But we can also understand that the surface state of, for instance, of gold must have a splitting due to the fact that we have a spin-orbit coupling in the bulk. So the surface state is also a direct result of the bulk spin-orbit coupling and can also be explained in that way. And it's not only that we have to introduce artificially such a Rashba term in order to calculate the spin splitting of the surface state. So therefore, I believe that one can now debate if this is really a topological surface state. So probably it's somehow a protected surface state. It follows the same terminology of this topological surface states. But I think what is really important to say is that the surface states can also be calculated using the entire band structure of the bulk, and that if you change the bulk properties, you will also directly change the properties of the surface state. So with this, I would like to move on to the second part which I would like to address, which is the formation of new 2D materials. And I would like to show you our efforts, how we would like to form stanine. So as I've seen or mentioned in the beginning, so these 2D materials like graphene for us in the beginning, of course they're interested, but what is missing for us is that this graphene-like cone has no real spin polarization which we can address. So the easiest idea if you want to introduce spin polarization in the system is that you have to increase the spin-orbit coupling in the material, and it was nicely shown by Jeff yesterday, is one way is just to go down in these group 4 elements, and because the spin-orbit coupling will increase with the Z number in the system. So silicene and germanium have been largely covered, and the next element in row is the stanine, so the 2D formation of a tin-like honeycomb-like superstructure or structure. And for these materials, a lot of nice properties have been predicted. For instance, that is a large gap 2D quantum spill Hall material, is a topological superconductor, and there are many, many theoretical predictions in this field. So therefore, we were aiming to trying to reproduce such a material on a 2D system. And this was basically the effort of one of our postdocs in the group, with Maniraj, who really digged into the literature and did a lot of experimental efforts in this material. And what we found in the literature, we saw that stanine has, for instance, has been already realized on the topological insulator bismuth telluride by the Zhang group in Stanford. But this already gave us some indication what we have to look for if we want to grow stanine on a different material. And to make the story complete, there's also been theoretical prediction that in general it should be possible to grow a 2D-like tin film on a gold 111 surface by another group. So what we then did is we studied the structural phase diagram of tin submonolayer films absorbed on a gold 111 surface for different evaporation procedures, different post-annealing procedures. And I don't want you to bore you with all the structural details, but I would like to focus only on one of these structures, which is the so-called HTY phase, which we think is most promising for the stanine formation on gold. So first of all, we start with determining the structure. So this is the low-energy electron diffraction pattern, which basically gives us the periodic arrangement of the tin atoms on the surface. And what we can do is we can analyze the structure by a simple fitting algorithm. We get a superstructure matrix, and from this we can derive a real space model of the periodicity of the tin atoms on the surface. So here we see in gray the position of the tin atoms on the gold atoms. I have to state it very arbitrary. We just put the atoms on top side, which we cannot say from diffraction, but it's the simplest what you can do. And if you connect these tin atoms, we see that they form what we call a distorted or compressed hexagon-like structure. So it's not a real honeycomb, but it's a compressed honeycomb-like structure. And when you go, for instance, in the publication of the Zhang group, who did the stanine on bismuth telluride, they also found not a really relaxed honeycomb-like structure, but they also found a compressed honeycomb structure, and they attributed this due to the commensurate registry between the adsorbate lattice and the substrate lattice. And as is here the same, since we have a commensurate structure, you can also imagine that the commensurability of the tin atoms with respect to the gold atoms are responsible for the compression of this structure. Then further on, we studied the electronic band structure. So here again, you see the band structure of the gold 101 surface. You see the surface state, you see SP bands, and here the D bands. And when we put the tin on top and go to the HTY phase, we see the formation of many new bands. So a lot of these bands are just due to backfolding of the gold bands, which are backfolded at the commensurate superstructure of tin. But here in the center of the Brillouin zone, we found a band which is not caused by backfolding, which is shown here in more detail. And when we analyzed the dispersion, we found that it's more or less a linear dispersion, and it leads to a very high that the dispersion state is very close to one would expect for graphene. To check if it is really a surface state, we changed the photon energy. We don't have a synchron available, but we did it in the lab. We went from the helium-1 line, which is about 21, to the neon-1 line, which is around 16 electron volts, if I'm not mistaken. And there again, we saw the state. And if we analyze the dispersion, we see that it's exactly the same dispersion. So this state has no dispersion in K perpendicular, and therefore is a surface state with a linear dispersion. And since it has already this morning been pointed out, if you want to talk about cones, we can not only have the dispersion in one direction, but we really have to do it in all azimuthal orientations. And what we then did is, this we have done with a conventional hemispherical analyzer, we rotated our sample around the azimuth and recorded a band structure. And as you can see here, you see these linear states, and they are there in all of our images for all rotational angles. And therefore, we believe that we really have a cone-like feature at the gamma point with a linear dispersion. And the last step, when we want to study the properties of our 2D tin-like sheet on gold, we went for not only for angle resolve, but also for spin resolve photoelectron spectroscopy. And the spin resolve photoelectron spectroscopy has been performed with one of these new type detectors. This has been also introduced. It's a so-called V-lead detector, where the electrons are scattered at very low energy at an iron oxide target. And this is a so-called ferrum detector of the company Focus, which is nowadays commercially available. And when we now take the spin polarized photoemission data with a spin polarization pointing in plane, and we take it for this cut here in momentum space and this cut momentum space, which is shown here and here, we see that the state has opposite spin polarization for these two cuts. And this is even nicely seen if you look at the spin polarization, which is the normalized difference between the number of spin up and spin down electrons. So for one side, we have a positive spin polarization. For the other side, here at the state, we have a negative spin polarization. So basically, what we can draw now is we can color this state. So we see that we have on the one side one spin polarization, on the other branch the opposite spin polarization. And since I've shown you that we have this cone-like dispersion, we see that, at least at these 2 points, the spin is going perpendicular to the momentum. So we have the spin momentum locking. And we are currently measuring this for different points here in momentum space, as this measurement is rather time-consuming. So to summarize this, we have seen that we have a strained 2D like honeycomb structure. We have a linear dispersion around the gamma point, and we have the spin polarized Dirac cone-like feature also at the gamma point. And these are, when we look at the paper of Zhang, these are also indications that we have at least a 2D Stanine line formation, or these are indications that we could have something that approaches a 2D Stanine formation on gold. And very briefly at the end, let me introduce to you the project which we have always started with. This is the functionalization of true topological insulator surface states by organic molecules. And this was a collaboration together with the group of Stefan Sanvito in Dublin. And there the idea was we take the band structure of a topological insulator, and they put an organic molecule, so this is H2 phthalocyanine on top. And what they can nicely do in their calculation, they can arbitrarily choose the absorption height of the organic molecule. So they can go from a physisorped state of the molecule to a weak chemisorped state of the molecule, and even to a strong chemisorped state of the molecule. And then they calculated the band structure using density functional theory, and then they projected the band structure on the quadruples of the topological insulator. And what you can see if you are in the physisorped state, you basically see that nothing happens. The Dirac point stays at the same energy. If you go to weak chemisorption, the surface state gets slightly shifted, so we have something like doping, and we have a new molecular state here. And if you have a strong interaction, we have even the formation of new states here close to the Fermi level. And in the experiments, unfortunately, we cannot arbitrarily choose the absorption height of a molecule, but we have to find molecules which reproduce this different interaction situation. And there we took these 3 molecules. So we started with the H2PC, which has been used also in the calculation. And we went to a molecule which mimics a weaker interaction, and to a molecule which was specifically functionalized in order to have a stronger interaction with the surface. And the strong interaction is basically induced by these sulfur atoms here in the functional group that were added to the H2PC. And if we do this, the experiment, we put these 3 molecules on the surface, we can indeed see what has been predicted. So for C60, basically almost nothing changes. So with C60, we can basically passivate our surface of our topological insulator and make it air stable for some times. If we would put H2 on top, we see that the Dirac point slightly shifted and we have this new state. And if we use H2PCS, so the functionalized H2PC, we see here these new states appearing here very close to the Fermi level, which also have the spin splitting as proposed by the DFT calculation. So in general, by organic molecules, we were able to passivate, shift, and alter the surface state properties of this topological insulator using specifically designed organic adsorbents. And with this brings me to our summary. So I hope I could give you an impression what we have done so far in the field of topological insulators. So we looked at noble metal surface states. We did momentum resolved measurements of the unoccupied band structure and compared it to calculations, which were performed in Dresden, and showed that the arguments of the band structure are also valid for the Shockley type surface state of noble metals. Then I have shown you our results for the absorption of tin on gold, and that we have indications that we are approaching a structure which is very promising for a stannine formation on gold. And then in the end, I've shown you our first examples where we put organic molecules on a topological insulator, and that we can passivate or dope or create new states by the absorption of these molecules. So as it was said in the beginning of the workshop, in the end, we should also, we can give an outlook, so what we think we could do next. And for us, since we are experts in the field of doing time-resolved measurement, our idea is, of course, to study the dynamics of the occupied parts of this unoccupied Dirac-like cones. And there has been a very nice publication recently by the group of Ulrich Höfer at Marburg, where they looked at 2 photon emissions, so the unoccupied band structure of a topological insulator, and they saw that just by using the right excitation energy, they could create an asymmetric population of this Dirac cone states here, or this topological surface states here. So in one direction, in K space, they have a higher population than for the other direction. And then they monitored the decay of this asymmetric population. And by monitoring this decay, they could differentiate the electron-electron interaction, which is an inelastic scattering phenomena, from the elastic scattering phenomena between these 2 branches of the surface state. And by this, they try to gain insight into the scattering mechanism of excited electrons into this topological insulator materials. And our idea is now, since we have a different view on the band structure, so we don't have energy versus K, but we have Kx versus Ky, for a constant intermediate state energy, what we would like to do is to monitor the transient population of electrons at a constant energy and monitor electron redistribution due to elastic or quasi-elastic scattering phenomena. And by doing this at different temperatures, we would like to distinguish between the electron phonon and electron defect scattering, and thereby learn more about this quasi-elastic scattering phenomena in topological materials. And as a last outlook, what is also possible, we are not only working with 2 photon emission, but we also try to look at optically excited phase transition. And from the field of ultrafast demagnetization, we know that if we hit our sample with a very intense IR pulse, we can somehow quench the magnetic order in the system. And one idea was, or could be, that we use a very strong excitation at the right frequency in order to drive the system of the topological insulator out of equilibrium. And one question would be, can we somehow act, for instance, in this graphene stannine-like way, can we act on the spin-orbit coupling, and can we somehow change the spin splitting in the system? And with this, I would not like to end without thanking all my colleagues, in particular the entire group of ultrafast surface phenomena group from Martin Eschlimann, also Mirko Cinquetti, who was with whom I strongly collaborate, and he was the initiator of this last project with organic molecules on a topological insulator. Of course, all our collaborators and you for your attention.